'Tis said that in the great temple at Benares, beneath the dome which marks the center of the world, fixed into a slab of brass, there are 3 diamond needles, each a cubit high, and as thick as the body of a bee. On one of these needles, at the beginning of the ages, God placed 64 discs of pure gold, the largest resting on the brass slab, and the others decreasing in size to the top. That is the Tower of Brahama. Night and day, the priests take turns transferring the discs from needle to needle, without deviating from the fixed and immutable laws imposed by Brahma. The priest may move only 1 disc at a time, and he must place this disc only on a free needle or on top of a larger disc. When in strict accordance with these rules, the 64 discs have been transferred from the needle on which God placed them to one of the other needles. Tower and Brahmins will crumble to dust, and the world itself will cease to exist.
In this afternoon's lecture, we're going to look at this problem, the Tower of Brahama, also known as the Tower of Hanoi, and come up with a way to estimate whether the world will end or not. For as was said in the video, if ever it should be that the priests manage to transfer all the discs from one pole to another pole without violating the rules of the game, the world will cease to exist. So let's find out if this is a real threat to all of humanity. But we have a warm-up problem, something to help get us in the spirit of the technique we're going to use to solve this Towers of Hanoi problem. These are triangular numbers. You can see that they form that each triangular number represents a different increment of arranging balls in a triangle or arranging objects in a triangle. The first triangle number is 1, because 1 is kind of on its own a triangle. Buy that if you like, don't buy it if you don't. But moving on to 3, it's pretty obvious that 3 make a triangle. Then 6, 10, 15, and 21. We can look at the construction of these numbers as an iterative or a recursive process. Think of the way that we might combine prior triangles with a certain number of future balls in order to make the next triangular number. Starting from 1, to make the next layer of the triangle, we add 2. Then to make the third triangular number, we take the second triangular number and add 3. To make the fourth, we take the third triangular number and add 4, and so on and so forth. This gives us a scheme that we can potentially use to construct these numbers easily. Displayed on the side of the screen, we have your first recursive function for the semester. What a recursive function is it's a function that uses itself to perform processing. You can see over there in the corner that we've called this function trec, and as part of trec's code, it actually calls trec itself. One thing that's very, very important to note here, though, is that trec isn't calling itself with the same argument that it starts with. Trec starts with n, but it calls itself with n minus 1. Why do we do this? Any ideas? Why might we not want to call trec n with inside trec n?
But if you don't change the argument, then it's sort of like an infinite loop.
Yeah, what will happen?
It's just the same function over and over again.
So assuming we forget to change the argument inside our recursive call, our program's not going to make any progress. It'll keep repeating the same thing over and over again. And like Einstein said, the definition of insanity is doing the same thing over and over again and expecting different results. So we are certainly going to have to change that argument over there. We also have to make use of the recursive call in some way. So the recursive call is the one inside the babushka doll, inside the large babushka doll. It gives me a prop idea for next semester. Another important feature of our recursive functions is that we have a base case. We have to have some way of ending and not calling the function again. So even if we change the argument each time, we still need to make sure that there's some way of telling the function, okay, you've run enough, you don't need to call yourself another time. This is up the top here in our function It's our if n equals 0, return 0. So what this function is going to do is it's going to start off with n, and then n is going to decrease with each recursive call until at some point, inside the innermost recursive call, n has hit 0, and then suddenly that one finally returns. It hits that return 0 statement. What does it return 0 to? It returns it to the prior recursive call. So that's a little tricky to understand. Let's look at the diagram to elucidate it a little more. Let's say we want to compute the 6th triangular number. Remember, our process for constructing a triangular number was to add, if we're looking for the kth triangular number, add k to the result of the prior triangular number computation. So let's add 6, which is our n there, add 6 to the value of the prior triangular number. So that's our Trec n minus 1. So add 6 to the triangle for 5. To construct the triangle for 5, we add 5 to the triangle for 4, and so on and so forth. When we get to 1, we're at our base case. We're at n equals 0. We can't go any further down, return 0. So that's the 0th one over there. And then our first triangular number is 1 plus Trec of 0. And then that returns. And what does that return to? That returns to T2. T2 is going to return 2 plus Trec of 1. And we've already finished calculating Trec of 1. So then that part's done. Now we're going to do it with 3. Return 3 plus Trec of 2. That's done. And so on and so forth, all the way up the chain. Let's take a look at what this looks like in a full program and see it operating. There we are, triangle.c. Let's make some more room for it. We have 2 versions of this code that we've written. One iterative version and one recursive version. What do you guys think? Put your hands on your head if you think all recursive functions can be made into iterative functions, and put your hands in the air if you think that some can't. A few more people, give a few more seconds. Hands in the air, hands on the head. Okay, I want one person from each to explain your view. Why do you think all recursive functions can be made into iterative functions and vice versa? Someone from that side. Who thought they could all be made into, or couldn't? We'll take either one first. And you've got about 5 more seconds before I pick one of you. Okay, you're smiling at me too large. What's your name? Bo Xiang. What do you think?
I don't know.
Well, what is it about recursion that we could potentially make in an iterative function? Is the information still being stored inside the computer somewhere?
Yeah.
Yeah, so when we run a recursive function, perhaps maybe if we could access the computer's memory and to get to the place of the variables that it's storing, we might not need to make a recursive version at all.
I agree.
That's good, because that is, in fact, the correct answer. All recursive functions can be made into iterative functions and vice versa. Now, it's not always wise to do so, and there are trade-offs involved in that we'll explore a little later. But the key thing to note is that they're about programming technique and programming style. There are stylistic reasons why you might want to use recursive functions, because they make your problem easier to understand, as we will reveal in a moment when we look at the code. But using recursive functions without intelligently designed structured code and careful thinking about the memory you use can also lead to strange errors that are hard to debug, and also to large amounts of consumption of memory and potential inefficiencies. So there's this trade-off going on. Let's see how this plays out in some actual code. I still don't remember the hotkey. Okay, bending up it is. So here is our iterative version. Start with a container variable that's going to contain our sum as we go along. Remember, we were keeping track of each level of the triangle, and from each level of the triangle, we add some more. And so this looks pretty similar to an ordinary iterative function. So if we keep track of how many we've gathered total, at each level, starting from the first level until you get to the nth level, add the number of balls to the level equivalent to the level you're on. So at the third level, add 3 balls. At the second level, add 2 balls. And we're starting from 1 plus 2 plus 3 plus 4, et cetera, and return it. We also have a recursive number. And you can see that this it's structured a little different. Here we have our base case, our case when we are ready to finish making recursive calls at some point when we want no more recursive calls to be made. And then we have our recursive call attached to a return function. Now, it is possible to make recursive functions where the recursive call is not tied to the return function, but this is often a neat way of writing your code. Let's give this a run. Ooh. And remember the tab trick from last time. Ooh. I'm not sure what a triangle is, but it should still run. I have never seen that error before. Well, it seemed to finish one way or another. Both of the methods produce the same result. I updated my Xcode last night, is the answer. Yeah, never update Xcode before class is the lesson. We can do the 7th number. Let's do the 35th number. Ooh. We'll try it. A few more. See, nothing particularly unusual there, except when I try put in a much larger number, the iterative version of the code worked, but the recursive version didn't. Does anyone have an idea why this might be? This is a bit of an advanced question.
All the functions in the previous one are still there, like taking them in.
Yeah, remember what we said about cleanup of variables for functions. The variables inside a function and the whole information connected to the function only get cleaned up when the function ends and when it's destroyed. So in the recursive function, one function's calling another function's calling another function's calling another function calling another function. And we have done this 475,000 times. So we have stored the information attached to 475,000 different functions. So we get what's called a stack overflow, the stack being the part of memory that's keeping track of all of these functions. The iterative version was a little different. It was only keeping track of, let's scroll up there and see. It's only keeping track of one function and 2 variables. So in this case, the recursive version ended up being an inefficient solution to the overall problem. But it gave us some hints as to style. Hao Chen asked, well, isn't there a closed form solution to this? Wouldn't 1 plus n times n on 2 be a more efficient algorithm? Yes, totally. And in one of my favorite lectures of this course, I think coming potentially at the end of next week, we're going to go all the way from a recursive solution, an iterative one using an array, and then all the way to one using a closed form solution that you'll be able to use to impress potential interviewers in coding interviews that love to use one of these problems, but often forget that some of these, yes, hey, Nicholas. These interviewers often forget that there are closed form solutions to many of the problems they might pose, giving you an opportunity to really shine. If you can show that you understand the trade-offs that are made between an iterative solution, a recursive solution, a solution that works fine for small numbers but not for big numbers, and then potentially even come up with a closed form solution for the problem that you're showing, you will shine. This is what was actually happening during our recursive call. Each of the functions were being stored on the stack inside the computer's memory. During the first call, for, let's say we're calculating the 3rd number in this example, for the first thing, when you call t underscore rec of 3, it starts up that function and loads it into the computer's memory. Trec of 3 then calls trec of 2, and that's added to the computer's memory. Trec of 2 calls trec of 1, all the way to 0, and now they're all in the computer's memory. And only when you get all the way to 0 do they start being deleted. So after the 4th call, the computer's going to pop that trec of 0 off and give the return 0 back to 1. When trec of 1 is now ready, thanks to 0 being popped off. The value of trec1 gets returned, and then we're done again. You can see why this might be both a clever way of thinking about problems, but also a potentially inefficient one if you're not careful when and where you use it. Now, we've discovered recursive functions, and we're ready to return to our monks and their tower. Let's see if we can solve their problem. So here's a video from YouTube showing what this puzzle actually looks like. The goal is to move the disks from the place that they started, where they're all resting bigger on top of smaller, and move them from the first pole to the next pole, to the last pole, while not violating the rule that at all times only smaller disks can be on top of bigger disks. In this video, there's a human solving it, but our goal is to get a computer to solve it and find out how efficient this is to understand if the monks with 64 of these disks and not just, how many are there? 3, 6, and not just 8 disks will ever complete the puzzle. And I think now we're going to move to the iPad, where we'll do an example of solving this puzzle by hand so that we have an idea of strategies we can program into the computer to solve it. Here are all our disks on pole A, and we want to move them all the way to pole C. We can see that if, let me switch this to presenter mode. We can see that if I start moving them directly, that's not going to work. That would instantly violate the rule that only smaller can go on top of larger. So what other option do I have? How can I solve this puzzle? Does anyone have an idea?
Move the yellow one to B.
Move the yellow one to B, then what do I do?
Move C back to A.
C back to A. No, not working. Okay, let's reset. What about someone else? I trust that you can solve this because there are many 5-year-olds who can. Let's run it back. Thanks, Liam. Remind me your name? Sarah.
They just put the red one on C and the yellow one on B. And the red one back on yellow. And green.
Now what do I do with the green?
On C.
On C.
And then the red one on C, the top.
Red one on C.
Oh yeah. And then B on A. The yellow one on
B on A.
yeah, and the red one on B. And the yellow on green. Yeah, on B. And oh yes, but the red one on A.
Red one on A.
Yellow on B.
Okay, let's give this one more try. Who can solve the 5-year-old puzzle? Any takers? Okay, Xinjiang, you get third shot at this. We'll try it one more time. And afterwards, you have to explain the strategy you've used. So I'm going to reset this. We made some progress last time, so we're certainly getting closer to a solution. What do I do?
Red one on C, yellow on B, red on B, green on C, red on A, yellow on C, red on C, blue on B, red on B, yellow on A, red on C, yellow on B.
Oh, yellow's smaller than green. So let's backtrack a little. Let's go here. Who knows the next step? We're close. Okay, pass it back.
On chat, it says red on A.
Red on A. Okay, we've got that from the chat. Who said that on chat?
That was Melvin.
Melvin. Okay, next step. We'll let Melvin on Zoom handle it for the minute.
Just let Zoom chat do it. You see the chat there.
Okay, Melvin, what's the next step? Green on B. Now what? Red on C. Yellow on B. Red on B, and we are done. Now, did anyone catch the strategy that was used to solve this? So anyone have a way of explaining what the process was that worked? Yeah, we've got, where's the microphone? Xinjiang, you've still got it? Or it's over there, okay. And what was your name? Evan. Say a little more.
So, like, basically you try to move a stack of a certain size for one thing. So basically you try to get a stack of 2 down B or C, and you get a stack of 3 on it. So basically recursively solving.
Yeah, and I think the microphone's off. Okay. No, that was on, you just weren't speaking into it. Explain that one more time.
So basically you just recursively solve the problem, but for smaller subsets increasing. So for this 4, you solve it for 2, and then for 3, and then for 4.
Okay, let's do this one more time quickly, and I'm going to do the recursive solution as Evan tells me which recursive problem I'm solving. So which recursive problem do we solve first?
So say we're solving the just one disk. So say you move red to C.
Yep.
And you move one disk.
Okay, so now we have solved the problem of Towers of Hanoi with only one disk. We've successfully moved the largest disk to the largest pole and not violated the rule. Okay, now what do we do?
So then you solve it for 2. So if you move yellow to B and then red onto C, then you solve it for side of 2.
Right, do that again, say.
Red onto B, sorry.
Yep, now we've solved the problem for a tower of 2.
And then A onto C, so green onto C, and then the red onto A, yellow onto C.
Yep, and now I'll fast forward through that. And now we've solved the problem for 3.
And then, yeah, move like red to C.
Yeah, and I'm not going to keep moving all the disks around because otherwise we'll be here forever. But Evan has successfully come up with this strategy, and you can see that we did this by a process of first manually looking at this, trying a bunch of things. It didn't work. We had some 3-year-olds in the audience, some 4-year-olds in the audience, and finally the 5-year-olds on Zoom chat got it. But let's see if we can actually implement this in code. And now we know the final technique for problem solving is solve the puzzle for n equals 1 by moving one ring onto an auxiliary pole, a pole that's not the final destination, but is the destination that we're moving it for the meantime, although for n equals 1, that's not so important. Then solve the puzzle for n equals 2, move the top ring onto an auxiliary pole, a spare pole, because we've got 3 of them, and then move the bottom ring onto the final pole and move the smallest ring on top. Then we can solve the puzzle. Now it's starting to get more complicated. 3 rings, solve the puzzle for, first move 2 rings onto the spare pole, move all the rings that aren't the biggest one onto the spare pole, move your largest one onto the final pole, and then solve the puzzle for 2. So the key thing here is move the largest ring to its final destination and then make a recursive call. If we're solving this for n equals k, it's exactly what I just said. Move the bottom ring onto the final pole and then move the smaller rings on top of that using our recursive technique. And if you don't know how to do it for k-1 poles, just follow the steps above. The intuition that makes this function is the fact that we do have this spare pole available to us at all times. This gives us room to solve the smaller puzzle while still putting the final disk in the place that it's meant to be. Let's check out what this looks in C. Now, this code looks a little intimidating because it does have these recursive calls in it with changed arguments, but you've just got to think back to our technique for solving. Move the largest disk onto the place it's going to be, and then solve the problem recursively. So now we're ready to scroll and see the horror. Oh, the horror! Okay, here we have our base case. If you are solving this for 0 disks, well, you've already solved it, just return. What about if we're solving it for 1 disk? Let's keep that in mind for the moment. So we know that any call to Hanoi itself will just return instantly. So for 1 disk, we move the disk from the place that, oh, this is going to get a little confusing, but we have 3 arguments to the function, from, via, and to, and that tells us that the first position in this is from that position is going to be via, and that's going to be 2. Even though we've used the, this is just for illustrative purposes. Actually, via and 2. This is what each of the places in the arguments represent. The first place is where it's from, the second place is via, and the third place is 2. But when we're actually running the program, we want to swap which poles are which when we do our recursive call. Because for our largest recursive call, the auxiliary pole is going to be different from the auxiliary pole for the second largest one. So we have to swap the 2 and the via in order, we have to swap from 2 and via strategically to ensure that we are actually solving the puzzle relevant to this particular recursive call. So let's go back here again and put, so from stays the same in this call. 2 and via are switched, and we're solving the puzzle for n minus 1. Now let's give this a run and see what happens. I'm sure we're going to see our weird messages again. We wait 5 minutes. Oh, no Hanoi.c. That's even worse. There we go. Oh, not so bad this time. Let's give it a run. Ooh, here's a new feature of the program that we weren't necessarily expecting. When I showed you the code, we accidentally skipped over the main function. In this particular instance, the function is asking us for something different this time. Rather than saying scanf, tell us what problem size you want to solve, it's asking for an argument to the program itself, to the program overall. Just like when we ran cat and t and grep, it took in an argument. For example, grep took in the search we wanted to find for. We have now written a program that also takes in an argument. Let's look at how we're doing this in the C code. Scrolling up to the top, I'm finally using this strange argc and argv that we had thus far just assumed away in our programs and are now finally including. I'll tell you what they are. argc is the number of arguments provided in the shell or on the command line to your program. So if I were to write down here, what would argc be in this place? Just shout it out. This is a quick one. 3. Okay, so let's print and see if this is true. And I'm going to make this program exit early so that we don't get to see the rest of the program yet. Oh, just do return. Oh, what happened there? Can anyone see what mistake I made? Am I in the wrong directory? That is probably the answer. Yes, I'm in the wrong directory. Now what mistake have I made? Oh, you guys should be better than this. You should be able to call that out quickly. Oh, there we go. argc is 4. Does anyone know why argc is 4 and not 3? So this is no fault of your own. You probably shouldn't have expected that. Why is argc 4?
I'm just guessing that dot/Hanoi is part of the counter as well.
That's fantastic and a perfect guess. Many times you are going to want to know what the name of the program was that was called inside the program itself. So the POSIX specification allows for a special value argument to be added. So the very first argument, argument 0, is the name of the program itself. And we can see this if we print out argv. I'm going to try compiling some code again, despite the fact that we have had some bad luck in this class. Now, don't worry about the syntax that I'm using to access the argument. We will get to that next week. There we go. You can see that the first argument was Hanoi. And this tells us what argv does. Argv is a container for all the arguments in the program. It is, in fact, what's called an array. There are similar kinds of structures in Python that allow you to hold multiple things in one variable. And we'll learn about those in the very next week. For now on, just keep it in mind that argc contains the number of arguments and argv contains the arguments themselves. So with that done, we can move on to exploring more of the program. So if argc is bigger than 1, a toy, argv1. Okay, I don't know what a toy does, so we know what to do when we're not sure what something is. Oops, we definitely don't want that open. Man, a toy. Convert ASCII string to integer. This tells us, if we think about it for a moment, that the arguments being fed in from the command line, if we're trying to convert something to an integer that was a command line argument, it's probably coming in as a string. So this tells us something else about arguments on the command line. They come in as strings, and then if we want to use them as integers, for example, as an argument to our Hanoi problem, we need to run a program that converts them, a function that converts them. And in this case, we see a toy is a function that does this. In order to use it, you have to include the standard library, include standard lib.h, and then we can read the description if we want to. And leave that to do at home. Is it going to complain again? Probably. Okay, we should be back to our regular function now. So it reads in, it checks firstly to how many arguments have been passed in. If there are more than one arguments, that means you passed in something other than the program name. So you've given it a number, then set n, otherwise print an error, print the usage. And then we're finally ready to run Hanoi with 3 poles named A, B, and C, and to solve the problem of size n. Let's finally give this a run. And we will solve the problem for 4 disks. Oh no. What did I do wrong this time? I actually know, but what did I do wrong? Didn't compile it. This is a problem that you will more than likely face at least once in this semester. When your code runs, but it doesn't do what you expect it to do, make sure you're in the right directory, make sure you're running the right version of the program, and make sure that you've actually compiled it. And Liam had a nice grok post on this, I believe, in the last 24 hours. How did you make that appear?
That was me. I can annotate the screen.
Oh, wonderful.
If you take the last command and do and /Hanoi, run the program and compile successfully.
Probably couldn't hear that, but if you missed that, it's on ed. So we can see our program successfully running our recursive algorithm, moving from A to B. And this should have formatted a little nicer. But the one way that this is working is you can see as these get deeper and deeper, we're moving deeper into our recursive call structure. So our pile of functions gets larger and larger and larger as the indentation gets larger and larger and larger. And we do this. by our fancy printf inside Hanoi, which prints the number of spaces equivalent to the depth to the size of n, which is also equivalent to the depth that we're at, or the inverse of the depth that we're at. Okay. I understand that this particular algorithm can be a little tricky to get your head around the first time. If you do have trouble with it, my recommendation is to actually do up a drawing like I made, either on a piece of paper or cut out 3 strips of paper of different sizes, download and run this program, and also step through the different lines of code while moving your pieces of paper around, and it'll become easier to understand. I might also post a version of last year's explanation that was animated, so it might be helpful. We're already screen sharing. And so how long will it take the monks to end the world? Now we have a program, we're ready to analyze it. This is what's known as a recurrence relation. It specifies the running time of a recursive function. You won't be expected to solve these within the course. However, we want you to have a familiarity with them and to understand what they mean. In this case, this is giving the runtime for computing the nth solution for the Towers of Hanoi. How long will this take? Well, it'll take as long as it takes to move 1 disk, so that's the +1, and also to move the n-1 disks onto the auxiliary pole, and move n-1 disks from the auxiliary pole onto the final pole. Remember, our strategy was to move the largest disk on, move all the disks, move all the smaller disks to an auxiliary pole, move the largest disk on one, and then move all the smaller disks back onto the final pole. So that gives us 2 times whatever it takes to solve the problem for n-1, because remember, a solution to the problem is equivalent to moving a pile of disks and then add 1 at the end. But unfortunately, this still doesn't actually tell us how fast this program runs overall. Well, what happens if we try writing this recurrence relation for t of n-1? So t of n was too hard. If we write it for t of n-1, we get this relation down here. Looks worse, doesn't look any better. What about for n-2? Same kind of story, definitely not making any progress. But we are starting to pick up a pattern. This is going n-3, n-4, n-5 in there. And what do we know about n that might eventually lead us to a solution? Can we keep going n-4, -5, -6, -7, -8 indefinitely? No, why can't we do that? Yeah, it'll reach 0. We only have n disks, so eventually we're going to get to our base case. We'll return to that in a moment. But for now, let's take our 3 relations that we've done for n, n-1, n-2, and let's substitute in the third equation 3 into equation 2. And we can do that because you can see t of n-2 is on both lines. And so let's just substitute that in. This is what we get. T of n-1 equals 2 times 2, et cetera, et cetera, et cetera. You can read it off. Now we can do the same thing, substituting equation 2 into equation 1. And we get 2 to the 3 plus 2 to the 2 plus 2 plus 1. And then that factor of n-3 connected to the 2 cubed. Well, this is starting to look like a bit of a pattern. Well, maybe instead of just substituting in 2 equations, we did this for n-1 and n-2. If this pattern holds, we should be able to substitute in t of n-3, t of n-4, t of n-5, as many as we have. This would yield us an equation of this form, following the pattern of substitution that we saw on the prior slide. So over here we have 2 to the 3, and if we substituted another one in, it'd be 2 to the 4, and then 2 to the 5, and then would have on the far side, the factors at the end would have 2 squared, 2, 1, or 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. So that gets us our pattern there. Now, knowing, what was your name over there? You said there were a finite number of disks? Brendan. As Brendan said, we can only do this a certain number of times, and we can only make it smaller n-1 times. So given that we can only do this that many times, let's create a new variable k. And this will get us all the way back to our base case. We know that we're going to do this k times. which means our final equation after having substituted in k equations looks like this, except I'm missing a substitution step there. You'll notice that after all of this, we still have t of 1. But we know that t of 1 is just how long does it take to solve the problem for a single disk. How long does it take? Only takes one step. So t of 1 is equal to 1, and we get this relation here. Now, this still doesn't look like a final running time. It still looks like a long sequence. It is, in fact, the geometric sequence, which for those of you doing some calculus and some linear algebra, hopefully you picked up on this one. But fortunately, it does have a closed form solution. It is equivalent to 2 to the n minus 1. It's equivalent to big O of 2 to the n minus 1, which gives us the final running time of our recursive Towers of Hanoi. It is O of 2 to the n. Now, this is a really, really large running time. Let's see just how large. For 2 disks only, we can solve it pretty efficiently. It took only 3 steps. For 4 disks, it took 15 steps. You saw when we were doing it on the iPad, it took us a little bit to actually figure it out, and it took a fair few steps. For 16, the number balloons to over 65,000. And by the time we get to 32 steps, we're over at 2 billion. So this running time explodes as the number of disks increases. So what about 2 to the 64? How long is that going to take us? 584 billion years for the monks to solve their version of the puzzle, assuming that they're moving 1 disk per second, which is a pretty reasonable estimate. So I think we can safely say that the world is safe for now. Come back to when I'm lecturing this in 583 billion years, and perhaps we'll be having a different discussion, or maybe you will be teaching the subject in 583 billion years. Hopefully by that time, longevity tech will have advanced. So my computer runs 2 to the 10 operations per second. Can it solve this version for 64 disks and do the printing out? Well, knowing that it does about 2 to the 10 per second, 2 to the 10 divided by 2 to the 64, that gives us 2 to the 54 seconds. That's still a pretty big number. So lucky world. Even if they were using a computer, this would take a very long time. And I think with that, yeah, we'll stop there for any questions, and then we'll move on to approximation algorithms next class. And that includes all of you on Zoom. Zoom says kindergarten puzzle. Well, I'm glad that a bunch of uni students could collectively, after about 10 minutes, solve a kindergarten puzzle. Yes. Yeah, so the reason why we're swapping from via and to is because we need to make use of the auxiliary poll. If we just say that the next recursive call is going to use the same via poll, then we haven't switched up the auxiliary poll, and that poll is no longer auxiliary. It's already storing our smaller disks from that call. So we need to say, actually, no, that's no longer the auxiliary one. The auxiliary one is now the one in the middle. And then when it's time to move the ones in the middle again, you swap it to a new auxiliary poll, and you keep doing that. Yes. Brendan, right? You'll have to shout. Void? That is next lecture. Stay tuned. With that, I think we're good for questions. Looking forward to seeing all of you tomorrow.